So today we're going to show that this function, f of x is equal to 1 over 2 pi sigma times e to the power of the quantity x minus mu squared minus divided by 2 sigma squared, has 2 points of inflection, and they are mu plus sigma and mu minus sigma. So that means that if you plug these points of inflection into the second derivative, we get out 0. That is one of the conditions for something to be a point of inflection. You also need to show that the signs of the second derivative change on both sides of these points of inflection, or that the concavity changes on both sides of these points. To make things a little bit simpler, we're just going to take the derivative of e to the negative x minus mu squared divided by 2 sigma first, because we're going to use that derivative a couple of times. So here, we're just calling a g. When we take the derivative of e to any function is e to a same function multiplied by 1 over 2 sigma squared times negative 2 and then x minus mu. The reason for this is because we have to use a chain rule. 2 sigma squared is just a constant, so we can move this to the front. And the power rule is multiplied by the exponent, subtract by 1. So that's why we have a 2, and this is a power of 1. So now we just simplify by bringing x minus mu to the front, bringing sigma squared to the front. The 2's will cancel out, and we still have this negative right here, and then e to the same exponent. All right, so now let's take the derivative of the original function. So 1 over 2 pi sigma is just a constant. So when we take the derivative, we can move it outside. And then we just have the derivative of this e to this exponent, which was the function g. And we already found that derivative. So we can just copy it down. So now simplifying a little bit, we just bring the negative to the front, multiply sigma squared times sigma cubed, 2 pi bottom, x minus mu stays as x minus mu, and then we multiply by e to the same exponent. So now let's take the second derivative. Here we're going to consider this quantity as one function and e as a second function. So that means that when we take the second derivative, we need to use a product rule. The product rule is you take the derivative of the first function, multiplied by the second function, plus the first function, multiplied by the derivative of the second function, which is g. The derivative of this function is just the derivative of the top, which is just 1. The negative goes to the front. 2 pi sigma cubed is just a constant, so we can bring that up. Multiplied by g, which is this function, and then plus, this we leave alone, times the derivative of g of x, which we did earlier, so we can just copy and paste that again, and then simplify again. Both of these terms have an e to an exponent, and we can just factor that out. This quantity here is left alone. So here we have x minus mu and x minus mu being multiplied. So that's why it's x minus mu squared. 2 pi sigma cubed times sigma squared is 2 pi sigma to the 5th. A negative times a negative is a positive. So now we need to show that mu plus sigma are point of inflection. So the first condition is when you plug them in, you get 0 in the second derivative. So it's going to turn out that we can actually plug mu plus sigma and minus sigma at the same time because of the square. So we plug it into the function that we found on the previous page. So here is our sigma plus mu being plugged in for x. The mu's will cancel out because it's mu minus mu. So we're just left with the plus sigma or minus sigma. Same thing for the E. We're plugging in mu plus sigma or minus sigma for x. The mu's will cancel. So we're just left with minus on the outside, plus or minus sigma squared, and then of course 2 sigma squared. Simplifying more, plus sigma is still plus sigma when you square it. A negative sigma squared is also going to be a positive sigma squared. The denominators don't change. Here we're going to simplify for E a little bit. There's a negative in the front, so that's why there's a negative right here. The plus or minus and square inside the parentheses just become positive because of the square. So that's why we just have a single sigma squared in the same denominator. Simplifying on the next line, we cancel a power of 2 for sigma on the top and bottom. So it just leaves us with the 1 on top. 5 minus 2 is 3. This first fraction doesn't change. So now you notice that these are the same fraction but opposite signs. So when you add them, you get 0. Here we have a negative 1/2 because the sigma squared minus sigma squared cancel. But 0 times any constant is still 0. So we have shown that when you plug in mu plus sigma, you get that the second derivative is equal to 0. So now you need to show that when you plug in these points, and then when you plug in points around them, you get opposite signs. So one way to do this is to pick a point in between each of these intervals and check what final sign your number has. So one way to do this is, for example, pick a number between or in this interval here. One example could be mu. If you plug in mu, you'll find out that this overall becomes a negative constant. So I have to put a negative sign. And you'll do the same idea for the endpoints. But there is a shortcut to this. So we have to really just look for the signs of each interval. You notice that this is just e to some exponent. So when you plug in real numbers or any constant, this is always positive. So overall, the sign of the function does not depend on this function here. It only really depends on this inner function here. And if you look, -1/2 pi sigma cubed is just a constant. This here is actually a polynomial because 2 pi sigma to the 5th is just a constant. This is in particularly a parabola. So if you think about it, what we plugged in before are zeros here for this parabola. So we found actually the solutions to this parabola or polynomial, which are these points. If this parabola here has 2 solutions, that implies, or 2 distinct solutions, this implies that it actually crosses an axis. The leading term here, because there's only one x squared in this overall, or in these 2 fractions, the leading term is a positive constant, positive 1. So that means it is an upward facing parabola, or like a happy face. That means that in this middle interval, the parabola goes below the axis. So that's why it's a negative. On the left interval, the parabola is above the axis. So it is a positive sign. Same thing here. It is above the axis. So it is a positive sign. So now you can see that on the left and on the right of both of these numbers, the sign changes. So it meets both conditions of being points of inflection.